So now we're going to look at how we can find the area between two curves using the fundamental theorem of calculus. What I want you to look at first is you see I've gone to Desmos and I've graphed y is equal to 2 times the square root of x and y is equal to 0.5x. The first, the square root, 2 times the square root of x is graphed in red, and y is equal to 1/2 x is graphed in blue. So what we want to do is we want to find the area that is surrounded or contained by these two curves, and we're going to look at it really just from 0 to 10. So you can see that even if we just counted those blocks, we would be able to come up with an approximation. But let's go to Excel, and in Excel I've given you just some words to this. I've said find the area between these two curves, and we want to go from x is equal to 1 to x is equal to 10. And so if you think about it just for a second, this would be x is equal to 1, this would be x is equal to 10. So this area all the way to x is equal to 1 is the area that we're trying to calculate. So the way that we do that is we take the area of the upper curve, and remember that would be all the way down to the x-axis, and we subtract from it the area from the lower curve. That would also be all the way down to the x-axis. So let's look at this in terms of using calculus. So what we do is the first thing that you're going to see me do is set up a definite integral. And the definite integral that I'm looking at would be from 1 to 10. Notice that I've rewritten 2x to the 1/2 minus 0.5x dx. And then what that means is I need to take and simply anti-differentiate. So when I raise 1/2 by 1, I get 3/2. I'm going to divide by 3/2. And notice that I have not simplified anything there. I do put the parentheses around it because that's going to help me when I go over to my 5 cell that I need to look at this. And then what I'm going to do is take and anti-differentiate the next part. And I know that, again, this is on the definite integral from 1 to 10. Now, one of the things that I want to mention is that sometimes you will see, especially in functions that are more difficult, you may see that you have two separate integrals set up. You might need parentheses around your entire second function, obviously if there's more than one piece, but I wanted to start with something simple. So here's my upper limit of 10, my lower limit of 1. You can see here I've simply typed in my antiderivative. Once that's typed in, I'm going to double click down, and then the last thing that I'm going to do is simply subtract my upper limit from my lower limit. So it looks like the approximation there is about 16. So let's see if we would agree with that. If we were going to just estimate the number of boxes, grid marks that we see between 1 and 10, it does look like if we counted them off, it would be approximately 16. So let's move on now to the second problem that I have. And the second problem that we're going to look at here says, based on current production techniques, the rate of oil production in 1,000 barrels per year from a certain oil well T years from now is estimated to be, and you can see that that's a rate, so I have it as R prime and C being current. And then we're going to have this additional, then we're going to set up a new system and we're going to call that new. And so we have the current rate and the new rate. And my question is, determine how much additional oil will be produced over the next 10 years if the new technique is adopted. So what I want you to think about there is, what should the higher limit be and what should the higher curve be? Well, because I'm telling you, or the question is implying that the new technique is going to produce more oil, that curve is the curve that we will consider our upper curve. And you could go into Desmos and graph this. I didn't for this, but feel free to do that. But what we want to do now is we want to take this information and we want to go ahead and look at it in a couple of ways. So what I did here was I broke it up into two different integrals for you. So what I've done here is I've really just taken the antiderivative of the new method, which would be r prime of nt, and you can see I've got an upper limit of 10, a lower limit of 0, because we don't have a year, a specific year, but over the next 10 years, so that would be from now 0 to 10 years out. So if you didn't do your antiderivative yet, you may want to stop and on a piece of paper go ahead and look at what your antiderivative is. But in one like this, we know that it's fairly straightforward. We simply have our original function divided by here, that 0.08, which would be part of our du. So we've got that antiderivative. We're going to double click that down, and we end up with the amount of oil production with our new method is 1,562.565, and remember that's in thousands of barrels. So we could simply multiply this by 1,000, move our decimal point over 3 places, and we would see that would give us millions of barrels. In the old method, we do the same thing. So here's my antiderivative for the old method. Double click down, and we can see that the old method is only going to give us 1,288.174 thousand barrels again. But the question was, determine how much additional oil. So if we take this upper area under the curve for the new method and subtract this lower area, that's going to give us the difference between the two production methods. And the difference that we get here is 274.3904 thousand barrels. So again, we could go ahead, multiply by 1,000, and see that we get 390.4 thousand barrels more using the new method. I hope that these two examples have given you an idea of area between curves, and there's certainly other things that you can look at in the folders that I've provided on Blackboard. We will move on to consumer and producer surplus next, and they are an application of this idea, area between curves.